The probability of event is what we're calculating in physics. That's the central question. And we discovered that there's a framework in which it can be done. It can always be written as the square, what we call an absolute square, which means the square of the length. Absolute square. Well, never mind saying the absolute. This line's supposed to say that. The square of another quantity, which we call an amplitude. And that's general. These things I'm telling you are general. I've only given you examples of it. That's the first problem. The next, therefore, the problem of calculating the probability is the same as the problem of calculating the amplitude, followed by one minor step, which is after you have the final amplitude, to find the square of it.
Can you go backwards? Take the square root of the square?
No, we talked about that. Well, somebody...
Because you got a plus minus.
No, it's worse than that. It's not a real square. It's the length of an arrow squared. The amplitude is an arrow. The square root would only tell you the length of the arrow. It doesn't tell you which way it's pointing. Okay? So there are two aspects of an amplitude. The amplitude is a sort of two-dimensional thing, and therefore you can represent it, it turns out, on a plane as an arrow. So an amplitude, it's a physical thing, was also as identical, that we use identical, we make it very equal by having 3 lines instead of 2. The same as these arrows that I've been talking about on a plane. And that's, by the way, for those who know mathematics, that can be equivalent to representing everything by complex numbers. You can do it algebraically, in other words, not just by drawing the arrows. But that's the business of whether you count things by picking beans out of pots or making marks on paper. We talked about that last time. I'm not going to go into this way of doing it, which is much more efficient than drawing the arrows, but we're only trying to understand what we're doing and not finding out the most efficient way to do it.
Why are you up?
I'm wired up, sir.
I know, but you're going in the wrong direction.
What do you mean I'm going in the right?
Well,
you see the wire? Do you see this thing?
I know, but it's going to. Right.
What do you mean? You got 2 of them?
Well,
all right, fine. Take off the other one then.
Can I take off the other one? Yes. Leave it on.
No, leave it on. Leave it on.
He says leave it on. Can you operate that way?
It's so heavy that I don't know if I can last long enough.
I forgot the microphone.
It's a very...
Leave it on.
Okay, here we go. I'm really wired for sound now. What I'm saying must be so damned important it's got to be recorded for all the time. Okay, we're up to here. Now the next aspect of the theory, therefore, would be to calculate amplitudes, and I would like to tell you the nature of the rules or the formulas that have been found for computing amplitudes. And there are a number of steps, a number of principles, and they're not very many. We've already got 2 of them, and there may be 4 altogether. So we're halfway there. The first one of the rules is that if a thing appears to be able to happen in more than one way, then we find the amplitude for each way and add. So if there were, I summarize that idea in shorthand by saying alternative ways, apparently alternative ways, amplitude, total amplitude, or final amplitude, or whatever, total amplitude. That means the final arrow is equal to the sum of an amplitude or an arrow. That's identical. Please excuse me, whichever I use, for each way. All right?
Isn't that vector sum?
I explained what that meant. Sum, add, yes, that way, yes. Now the next step in this summary, I'm only making a summary, and you know all the answers. You were here the time before. Add. How do we add? As follows. If you have 2 amplitudes, there's 1, then another amplitude 2. The way of adding them is to find out the net result. Think of them as steps. Think of them as steps. Amplitudes are like steps, and the sum is the total walk, so to speak, made by the steps in succession. Net step equal to the sum of the steps in succession. That's a way of speaking. Result of all the steps in succession. That's if someone's taking notes, That's the way of saying it. And the net result of that is mathematically also, geometrically. I mean, you draw one arrow, and then you draw the other one, but you put its tail on the nose of the first one. That's arrow number 2. Then the final sum, or total, would be the step from the initial position all the way to the final. Damn it. It's supposed to be straight, right? Actually, the line doesn't mean anything. It's from here to here that we have to say is a step. And that's the total in this particular case. And of course, you can add any number of amplitudes by taking more, the same idea, right? All right, yes?
When you had the and then you had the first one and 2 in blue, why did
Yeah.
they come out of the same?
Well, I always use the same position to represent the way these amplitudes look. This is a convention. I always start them from the same place to define them. But when I add them, I can do a geometrical trick of putting the one tail on the other and finding the net result, okay?
So those would be the alternatives.
This is the amplitude for one alternative, and this is the amplitude for another alternative, and this might be an amplitude for another alternative. And by adding them, we just imagine what would happen if we considered these lines as steps. That's the process of adding. We're going to find another process of multiplying later. Do not fret. I shall explain it with equal obtuseness or lack of clarity as I did that. Now, to give a quick example and to remind you that a very simple physical circumstance in which something can happen in more than one way is if you have a thin layer of glass and you have a source of light and you're trying to detect whether the light comes from this thing by a photomultiplier detects photons, and you want to know whether a photon will arrive here, you say, it appears that the photon can get there from one of 2 ways by normal logic, but we're not going to say it does it one way or the other. We're going to say there's an amplitude that it does it one way and an amplitude that it does it the other way, and we compute the probability by adding the amplitudes and then squaring. I didn't say what squaring was. I'd remind you, by squaring to get the probability, that rule is if you have an arrow for the amplitude, you just take the square of the length, or what's equivalent, the area of a square, of which this is one side. The position of the square means nothing, just the area is what counts. That's the squaring. Okay, those are the operations. And in this example, we've been exhausting ourselves with, we've seen it so many times now, we say, well, maybe the photon comes down to here and goes up to here, and maybe the photon comes down to here and goes up to there, and we have to calculate an arrow for each one and add them. The rules for calculating the arrows in this circumstance depend on the color of the light and the position of these things and so on, and they're less general than the part that I've written so far. What I've written so far is very general for every problem. If the thing can happen in more than one way, you find an amplitude for each way and add them by this process. We last time also told how to find the amplitude for these ways in a particular example of light. And for that example, just to remind you, if you want, that the special rules of front reflection from a surface of certain kinds of glass produces an arrow whose length is 2/10. This is much more special, as you can appreciate, than the rules before. So let me separate the general rules from the special rules with this line. And so the reflection from the front is 2/10, and from the back is minus 2/10. I've thought about it while I was falling asleep, and I think I've got it backwards. I think the front surface is the one that's the minus, and the back surface is the one that's the plus. I can't remember right now. Maybe when I'm doing some other problem, I'm going to get into trouble, and I'll have to reverse it. Perhaps I reverse it now. I'm saying it's the other way so as to confuse you completely so that I'll be right one way or the other, either yesterday or today. Whereas if I do it consistently, I might be totally wrong. Therefore, in order not to be totally wrong, I make up the rule that the front surface is the negative. It goes backwards, and it's 1/5, whereas the reflection from the back surface goes forward. You'll, of course, appreciate that with the qualitative way we were analyzing it last time, it doesn't make any net difference. It just turns all the arrows over. That's the back surface. This is what happens to the front surface and the back surface, but in addition to that, we have to rotate the arrows through an angle which is proportional to the total time taken to reach the detector from the source. So you'll have to in addition to this, you rotate. I love all these colors, but the problem is only one of choice. So I get dull. Now you must rotate arrow through angle which is proportional to the time. I said it, but we're not going to do it for a while. When the light of different colors, it's the same rule, but a different color has a different coefficient of proportionality. That is, it goes faster with time for blue than it does for red, but we'll just work with red now. One color. And we analyzed what happened with this thing under those circumstances and did some other problems about a mirror and so forth last time. Now, are there any questions? Yes?
I'm a little confused about the rotation in time.
Yes.
If you said yesterday that you can rotate like 1,000,000 times. or something.
Yes, more than that, in fact.
The direction that the arrow ends up in
Yes,
is, could it have gone around 5 times and end up this way? And
Yes.
100 times and end up
yes,
this way?
it could end up in the same position because
So
it went.
how do we know the difference between
We
those?
don't. We don't have to. We just want to know where it ends up. We don't have to know how it got there. It's true. If you want, you compute it by turning it 6 million times around plus 1/8 of an extra turn. That's why some things looked confusing when I had small differences and so on, because the tremendous numbers of turns that come from this distance to here and then to here. But if this is a very thin layer, there's the same tremendous number practically, but just a little bit more. So one went around 1.5 billion times and ended up here. The other one 1.75 billion. So it's only a quarter of a turn different. So all I really have to worry about for that experiment to figure out the probabilities, which don't depend upon the absolute position of our triangles, but just the length of the arrows, is just the spacing here is what counts, it turns out, not the spacing from there, in that experiment. But it is possible to do an experiment in which you would have another mirror or another surface here, and it bounced back to somewhere else. Or you could have these things so far apart that there's 1,000,000 rotations different between what happens in the back surface and the front surface, and still it works, as long as it's accurate, that you can keep track of the 1,000,000 accurate enough, that the bottom isn't vibrating, and every time you do the experiment it's slightly different, because the 1,000,000 is very hard to keep accurate, steady, because if you changed anything, it would be a little bit. 1/10 of 1% more is 65,000 more rotations. So you lose track if it's a lot of rotations, if there's any irregularity in the apparatus. But if you make the apparatus very carefully, you can find this kind of interference in which arrows have turned as much as 10⁷ or 10⁹ times around.
Doesn't the electron multiplier time resolution have to be extremely high to get that angle?
No, we're not worrying about that. We're just calculating the probability that the detector goes off. What you don't appreciate, this source has to be on all the time. You really don't know when this thing was emitted from this source. No, you don't have to have precise resolution, because you're asking for the probability that it goes off. We're not discussing time now. We just turn it on and we wait and it goes click, and we want to know the probability that it goes click. Not the probability it goes click at a given moment, but that it goes at all. All right? It doesn't require precise resolution, no. Better note. The amplitude to arrive here at one time and another time differ only in that the net triangle will be turned a little. But the probability is always the same. If I were to calculate this for a later time, say, I would make my arrows turn, all of them would turn a little further, but the size of the resultant would be the same. The probability is constant in this problem. So I don't need any resolution accuracy to analyze it. Okay?
So is it that when it ends up, in other words, if
Yes.
if the alternative, the two alternatives was one had turned around 1,000,000 times and the other one 1,000,002. So all we have is 2 times difference, okay? And then
No,
the
2 isn't much good, but, well, yeah, all right, 1,000,002 times, okay.
And then the next one is 3,000,000 versus 1,000,002.
No.
Okay, what would,
What's the next one? What do you mean by the next one?
I'm trying to set up 2 separate cases.
Experiments, yes,
Right.
good.
And I want to be able
Okay,
to see
let's-
or ask you if by looking at the arrows at the end of it, if I can tell which one has 1,000,000 difference in rotation versus,
No,
okay. Because
You
that's
cannot.
how it works and everything.
no, you cannot. With this particular experimental setup, if you had another case in which these two things are much further apart, I haven't got enough room on the blackboard to do it the proportion you asked me. And I had the same detectors and so on. But I had this adjusted just right. This is exactly a definite number of rotations more than this. then all the arrows would appear in the same position when I was done, and I can't say how many times it went around, all right? And in fact, the probabilities show that. The probability of reflections is a curve which ideally just repeats, and I don't know when I find the thing here, whether it was on the third bump or the second bump, unless I look at the other aspects of the apparatus. All right? In practice, because if I had used blue light, or slightly red or bluer, a little shift in spectrum, the angles that are turned for a given distance are different, then this curve for another color that's only slightly different would be, say, let's say it was very slightly redder. Then the curve would go like this, you see. It would be just the bumps would be slightly further apart. And N does, I didn't make it too slight, it's there. But you'll notice that after a bit, the bumps of this and the crests of that are on top of each other. So that if the light that you're using is not perfectly monochromatic and has a little mixture, so that it may have been a photon of a different color. If we have too big a thickness, we don't get many bumps. We don't get them anymore because they're smeared out by the possibility it was a perfectly red photon or a slightly different color photon that we were receiving, and it gets all smeared out. For thin layers, however, slight differences in the color don't make much difference. Therefore, to see this out to 1,000,000 times requires a very, very careful design of a source that permits light of exactly one color, such as a laser, for example. I also would like to add that this is the same for all particles, the same principles, this stuff, and the adding of the arrows and so on, whether it be light or electrons or neutrons or atoms or anything else. These same experiments, or the analogous experiments can be done with neutrons, a neutron source, a neutron detector, something that scatters neutrons. The formulas for the degree to which the angle turns is not the color any longer, but the energy of the neutron. It's actually the energy of the photon also, so I could put it in a general form. But the neutron can change its energy easier than a photon can change its color. And there are small differences in the situation, but the aspects that I'm explaining are more general. Now we've got me tied up by several wires, and now it's simply a problem of keeping myself extricated from the...
That could go in your pocket too, maybe.
I'll try it.
What about X-rays?
Same, X-rays are photons, the same. They're exactly the same. They are. What is the difference?
But your mirror is different, right?
Well, to be more effective, actually it would work, but it would be very weak. The .2 is too small for X-ray. But it can be done, yes, with X-ray. The only difference between light and X-rays is the color. We start with the red. That means a certain rate of turning of the amplitude, the angle, as we go through distances. With X-rays, it turns very, very much faster by 1,000 times, or 5,000 times faster. That is, the distance you have to go to make one turn is faster. A photon, therefore, you could say a same photon could be red. I mean, not the same photon, but photons can be red or yellow or green or blue or violet or ultraviolet. That's faster than we can even see anymore. Our eye isn't sensitive to it. Or far ultraviolet would be much faster. Very far ultraviolet is the beginning of what we call soft or low energy X-rays. Then they get to be hard X-rays. All of this is faster and faster cases in which the photon arrow is turning faster and faster, okay, per inch or per second. And on the other side, it could be slower, and that's called infrared or very far infrared or heat waves, and finally radio waves. They're all the same thing. It's just the speed. They're all photons of different colors. They're all the same thing. It's just different colors. Our eye is only sensitive to a very narrow range of possible colors, so to speak, and the entire enormous range on each side is detected by instruments, and we call them by other names just to, because they have very apparently different properties, because one or another aspect is emphasized, but they're exactly the same object. Yes?
I'm curious as to what you mean by a red photon or a blue photon.
I mean a photon which in this particular apparatus looks red. That in this particular apparatus, it means one in which when you go to calculate the amplitude, you have to rotate the arrows at a particular rate, which is, I have to get some numbers for that particular photon. It's,
That's nothing that could ever be empirically determined.
I just told you how. look at the interference here and find out how far apart they have to be in order to get a maximum reflection.
But if you don't have a monochromatic field,
I said I had. If I haven't got a monochromatic field, I can't tell you what the color of the photon is. You didn't tell me what the situation was. I said in this experiment that I had carefully prepared a special source which had only one color photons coming out of it.
no, but when you're talking about the superposition of the two.
I said, then I
you
can't.
talk about a blue photon or a red photon.
I suppose then that I had a source which had one and then another source that had another, or a source that had different kinds coming out. Then I can't tell which it was if I'm out here too far. If you have two different things, you can tell. What's the question?
Okay, in the case, in the experimental situation, where you have both red and blue photons,
Yes.
say possible.
Yes.
In
Yeah, let's say we had a dichromatic source. That had,
anytime you detect,
we had a dichromatic source. We had two kinds of
Right.
possible photons.
anytime you, out there, the
And you
detector, you
detected
get a
something.
click.
Yes.
There's no way to tell.
No, there
if it's
isn't.
a red or blue photon.
No, you can't.
Okay.
Right. It is, huh? No, not it. You're the one who had it. If this has got a very, very fine time resolution, you can't tell. If it's very sharp. And I'm trying to make idealized instruments. If you wait a while and do some things which involve time, then you can build this so it reacts differently to red and blue photons. Because they're turning at different rates and you can make interferences, so one is more sensitive than the other, okay? So you can make a device which could separate them, but that would be using more time. And my things are idealized. It's supposed to be at a point at a given instant. All right? I'll come back. We haven't talked about time here much, and I'll come back and talk about time maybe today, a little later. All right? Okay, how are we doing? With the most important part of this is these principles up to here. The specific rules, in fact, you'll be horrified to hear, I'm going to change. We're going to understand them in a more deep fashion as different rules, as consequences of still other rules that are simpler. They are already. Just like the 1/5, that's just going to be the result of an enormous mess. So glass is a mess, so how could 1/5 be anything simple? So these particular principles are going to be altered a little bit. But I want you to concentrate on understanding this aspect, that physics is turned into a system for computing amplitudes. Desired are probabilities for events, but amplitudes serve to produce probabilities in a simple manner, namely by looking at the square of the length, I mean. So we have to discuss the framework for computing amplitudes. In complicated problem, the amplitude can be calculated by resolving it into simple subparts. If we knew how to compute the amplitudes of simple subparts, if we had some rules of combining them, then we can do any problem. And physics has discovered that it's possible to simplify the world and to say only certain kinds of things can happen for which there are definite amplitudes, and there are ways of compounding the amplitudes to say that a more complex process is a superposition of a lot of different things that could be happening in certain ways, and we have to put those amplitudes together. The first principle of composition is this one, that if there's more than one way a thing can happen, you simply compute the amplitude for each way, disregarding the other way, and add them together as advertised. Right? Now I wonder before I go into the next rule, which would be logical to do, to tell you the other way of compounding the things, so I prepared your minds to be ready for that. Unfortunately, I want to show you something else in between. Because in the examples that we had of the mirror, there's another beautiful example of your idea of cheating the world by making those slots was fun. And I want to show you another example of something which involves such cheating, which is not, still only uses the rules that we've written so far and doesn't involve the new rule of composition, which I'm going to talk about in a few minutes, which is called multiplication.
In that slot experiment, how far out can you make the slots away from the center?
Slots. As far as big as your mirror is.
And can you go a mile?
Yep.
And you still get bright?
Yep. Again, the same difficulty. If you go a mile and your light wasn't absolutely monochromatic, it doesn't work. Because,
Right.
yeah.
Okay. Follow that.
Right. This, a mile with real light is not really practical today. The lasers are very good, but they're not that good.
100 feet?
Yes. Now, the thing that I wanted to discuss was another one to show you that not only can you from the point of view of these amplitudes, understand that light reflects at equal angles from a mirror. But even the idea that light goes in a straight line is not directly the way we're going to do it. We can think of the light as being possible that it goes in many different ways. If this is a source, for example, and this is a detector, and there's nothing in between, well, let's to keep the world finite, let's say there's a little hole so that we don't have to talk about things that go too far afield. This is some kind of black junk. How black junk works is another question, but never mind now. Now, I would have said so far that the way I've described it, in this situation, if we wanted to get a photon there, you say, oh, well, it goes in a straight line here, and the amplitude would be the particular arrow, and there's nothing to interfere. There's only one way. It does turn out, however, that if you wanted to, and you can do just this way, you can say that the light maybe goes in some other path and comes and has an arrow for every possible way it can go. And all those little arrows are at different angles, because the time it would take to go this path is longer, and so on. And you add all those arrows, and as usual, everything cancels out. And the only part that counts are the paths very close to the straight line. Let us see how that works. You say, well, that's frightening. There are so many possibilities. All right, if that's frightening, let's decrease the number of possibilities by imagining that we're not going to take every possible curve, but just a special kind of sub-example. Suppose that I were to say, and I draw a dotted line here, arbitrary place. The fact that these screens are there are not important. And I say something like this. Let me suppose, I don't know that light goes in straight lines, but I'm going to imagine I know that it goes in straight lines at least to here, and a straight line to there. Let me show that what happens and why it looks like it goes in a straight line all the way through. Suppose that I would imagine that the possibilities that exist are that not only that line, but also one like this. Or another possibility is it goes like this. And of course, there are others on the other side. All right? And I play the usual game. I calculate an amplitude to go this way. Of course, the distance is longer and the time would be longer here. And here, by the way, everybody knows is the shortest distance and therefore the shortest time. So, huh?
This is identical to the mirror problem.
Thank you. Thank you. This is identical, therefore, to the mirror problem. Because if I would represent distance this way on a graph, I'm going to turn it, see? I'm sorry to make the, well, maybe I could make the graph this way, yes. Make the graph this way and measure the time this way that it takes. Then the path that's in the center takes the least amount of time. I mean, I got a graph with paper tilted at one side. And this path takes longer, this path takes longer, so it'll be a similar kind of curve for the paths. And we'll have exactly the same business of adding arrows with ever-increasing twist as we went off, and only the ones that had the same time contribute strongly, and most of the contributions from the center. Then you can play your game here. You could put holes and slots and get a much better intensity of light here by making such a disk with slots. They would be circular, actually. If you think about the other dimension, which we haven't talked about, they would all be equal time on a circle, and so you'd make your slots in a circle. It's called a Fresnel disk or something like that, or zone plate or whatever, and it works. I mean, people have made these things.
They're used in lighthouses.
No, that's a different kind of Fresnel lens, unfortunately. The same man has got his name on two different things. But now I'd like to show you a different way of cheating.
And those ones work correctly.
Yeah, here's the way I want to cheat this time. In this particular case, let's suppose that those little slots, these things, occurred up to here, and here. In other words, the whole brown, black, what does it make? This is the edge of that. That's as far as I'm going to go on each side, okay? Now let's say those times are equal like that. Now what I want to do is I'm going to increase the time for the central light so it's the same as the time for this one, and increase the time for this light so it's the same, and increase the time for all the light so no matter which way it goes, it takes the same amount of time. Okay? Then all the arrows would have the same time. They would all be in the same direction. We'd get a terrific amount of light there, much more than we would get if we had an open hole. Can we get more light here than an open hole? Yes, sir. Watch. All right? Watch now. Damn Okay, excuse me, that shouldn't be recorded. Now, okay, now, how can we make the time longer? You remember that light goes slower in glass. So if we were to put a piece of glass in here of just the right thickness, let me make the glass in red. I'm going to put a section of glass here. I'm going to make it go through glass here, which is just thick enough that it slows the light down long enough so the total time it takes to go through the center is exactly the same as the time it takes to go way up here and down. You see, of course, if it goes up here and down, it does that all in vacuum or air. We'll say vacuum is the same as air. And that's a longer distance than this in order to keep the race fair. They're all racing, okay? To keep the race fair, we slow down the guys who try to go through the middle. See? Okay. So by slowing them down, that means they take a longer time. So that this time has been moved, then we're going to move it up to there. So that it takes the same amount of time as the fellow at the edge. And that takes a certain thickness of glass. Now, how about somebody in the intermediate place? Like this. We're also going to move him up to the same place, same time. But we don't need as much glass. That is, the delay, the extra time, is less for him than it was for the front one. And therefore, we'll put a piece of glass here in that's not as thick as the piece of glass that was there. Likewise on the bottom. And of course, when we get near the one at the top, we hardly have to move him at all. We have hardly to put any glass at all here. And we want it that right thickness at every distance. The best way to do that is to construct a piece of glass which is of this shape. All right? And then we will discover that a light source here makes this photomultiplier go off very much more probabilistically, with a greater probability than it would have done if there was no piece of glass there.
But now you've got a reflection.
I also happen to have some reflections. They're not important, it's more complicated. But the main feature is that we get a much bigger intensity to this point. You see why? Because the arrows, which were coming in at different angles and undoing each other's effect, are now all coming at the same angle and the whole thing accumulates. I'm sure you all recognize what this piece of glass is. It's a lens. And a lens which focuses from this point to this point. Not only that, you've suddenly discovered something. How to design a lens that goes from this point to this point. How thick must the lens be at the center compared to this edge? Easy. It's got to be just that thickness to slow the light up the amount that would correspond to the difference in the time.
That's pretty.
So you know all about lenses and the film, huh?
Very nice.
Yeah.
You could also take that curve on the graph and make the lens with a flat side on the other side. And that just
Oh, sure you could. I mean, the fact that I made it, put the pieces in the center is not important. We can put the glass over here. Funny kind of lens, all right? Or we can make one side of the lens flat and the other side curved. We just need the same thicknesses, that's all. We just got to get the right thicknesses. So that's another example, and I couldn't resist showing you that because it's a nice phenomenon that everybody knows about, that lenses concentrate the light, but that our arrows predict all of the simple-minded things it'll turn out, because this is it's been tested, it's the right theory of the world. It works with all what we know in the world, and it works therefore with the things that we knew before from a different point of view. All right, is that okay? Yeah. Yes.
If you didn't make your lens absolutely perfect,
Yes.
or off by half a wavelength of light
Yes.
in distance, then would it be as if there were no lens there at all?
Let's do the following, which is similar to what you're asking. Instead of changing the lens, let me move away from the focus. Let me say that I moved the photomultiplier to this position over here. I tried the experiment over again. With exactly the same lens, if you don't mind. It's not what you asked, but I want to illustrate something else. But the center is here. So now, because although I had the times exactly equal for here, the times won't be equal for there. For example, let's take the ones that happen to go along the edge here. I should do it in another color because it's a new experiment on the same diagram. So let's take it. This part's the same. But this one would be going to there, see, instead of to here. Whereas on the other side, on this one, it goes to here, but this one goes to there instead of to here. Now, before, these two were equal. Now they're not, although it's hard to see on the diagram, but common sense shows this distance is longer than that. And therefore, the times which had been previously all constant, now had them with the original lens all nicely arranged this way. It turns out now, with the new one, the Brown experiment, one is a little bit ahead at this end and the other is a little bit behind, and so it's sort of tilted at times. And that means that the arrows don't come out all straight. As a matter of fact, they slowly turn and they have different angles as you go along, and you can make it so as you go all the way around it comes back to zero. It's this big circle instead of a straight line. That is, instead of having all the arrows exactly in the same direction as we did in the original blue, this original case, gee, it's funny, the blue looks tilted and the brown looks straight now, but I want the brown to be tilted. When the brown one gives a sequence of arrows which are always a little different when you add them together, and they could be arranged, the simplest thing, I mean the first thing that could happen is it could add up to nothing. The first time it adds up to nothing, how much tilt do we need? We can work that out. It just is that amount of distance in which this extra distance corresponds to one rotation. Then there's no more light. So if you put a screen here to look instead of a photomultiplier, you'll find a patch of light whose size is not one point, but has a certain size. It gets a dark ring at a distance out from the center, which is just that distance where this time is one rotation longer than that time. So if you look at, with a very good instrument or a beautiful photograph, very carefully made, of the image of a point source of light in a lens, you'll find it's a circular patch with a black ring around it, with a white ring around that and a black one around that and fuzzing out. Why? Why the white ring?
Refraction images.
But why?
And a little further out, you went around.
Yes, because if we tilted it further, then we could go around and not, let's say 1.5. That gives us a reasonable, something left that's not quite zero. So it goes up and down, much like bumps did with the other example, but they're not all the same height because these circles are getting tighter when we make the angles change quicker, so that the bumps get smaller. In other words, you see a very bright ring, then dark, and then a slightly less bright, a very bright spot in the middle, dark, a little bit less bright circle, dark, still less bright circle, dark, still less bright circle. Peters out. And maybe you've seen it if you happen to have had the experience of such pictures. I didn't bring one.
One of the things that
But all this is nice. It explains everything we see very nice. It describes everything we see very nicely.
one thing that question suggested is that possibly you might have to polish that lens to within a wavelength, which isn't true. If there's imperfections in the lens, it just tends to fuzz out that.
Yes, it fuzzes out the image. That is, if you make, it depends on how. There are ways of making this lens cockeyed so it doesn't work at that particular place. Not only fuzzes out the image, but if you included the fraction, the dead center part happens to be black, but there's a white spot very close over. Just like this, it would be as if I made the lens wrong, so it was supposed to focus here, and you put the instrument here. It looks like a good lens, it makes a focus, but not where you thought it was going to make it. So you can get all kinds of distortions and
The point I
complications.
was trying to make is you don't have to polish that lens to within a perfect wavelength in order for it to work on the average.
To work more or less, you're right. Yes, that's true.
If you use a pinhole there, you get the same thing.
Pinhole where?
A pinhole camera kind of thing, where you're putting your laser through a pinhole, and then you look at the image of that pinhole.
You get a different kind of thing. You get a thing, but it's not the same thing, okay?
Okay.
What happens there is the pinhole is not a pinhole. A pinhole is not a point. And I'll do this quickly because I don't want to, but you have this screen and the source back here, and you ask whether you get something on a screen over here. That's your pinhole.
Right.
What happens is you get an interference between the photons which would go through this place and the photons which go through this place, because the pinhole is not exactly a point, and that produces a pattern over here. It's not exactly the same as that pattern, but it's calculable and somewhat similar. If the pinhole was made smaller and smaller until it's small compared to a wavelength, so the differences in the distances to any point on the screen is less than one rotation, then all you get is light all over the screen. You don't get any pattern. Okay? Small enough hole, no pattern left. Okay? All this stuff, you can understand a lot of physics this way, even though it's a fluky way, making arrows. All right, now, next. I want to advance. If everybody's with me, I'm going to advance to the next stage in the analysis of such problems, and that's this. Oh, we talked about total. I need some space, so I'm going to have to erase some stuff that was equally important. I mean, if you only could erase that, only unimportant things, you still haven't got enough room on the blackboard. But I'll leave this part to tell you that. But now I would like to explain another feature. There's a way of thinking about the photon that was coming from our surface here, which said it came from the source and went down here, got reflected, and came up here. You can think of that as 3 stages in succession. It goes from here to here, it gets reflected, and it goes from here to here. The other case, the amplitude went down to here, and so I'm not worried about the other case. I know how to sum them. I'm taking one alternative, and I'm breaking the alternative into a series of successive steps of operations, things that happened in succession. First thing, it went down to here, then it got reflected, then it went back up to here. Those are 3 stages, 3 steps, I might say, 3 ways of sub-parts of the description, and it works. You can do that. You can say, and you'll see in a minute how it would be. I'll try to give a rule for it. First, you rotate it a certain amount due to this amount of time, and forget it for a moment for the reflection. When you come back, you have to rotate some more. So I could break that total rotation into 2 subparts. I could say, well, you rotate for a while, and then you rotate again. Also, the reflection can be thought of as a shrinking of the arrow from size 1, which it would be if it wasn't reflected, just coming from the source, to 1/5 size. So you can think of it something like this. I rotate for a while, corresponding to this time. Then I shrink the arrow. That corresponds to the reflection. I actually discovered I ought to not only shrink it, but turn it backwards. The front surface, I say, is backwards. And then I must rotate some more until I get to here, depending on where this is, right? Wherever it is. That is, what I mean is I made these distances equal, but they didn't have to be equal. I rotate corresponding to this distance, I shrink the arrow, and I rotate to here. And I'll get the right arrow. So I can analyze the arrow as a series of steps, which sound like this. Rotate, shrink, rotate some more, and so on. All right? Furthermore, I could, in fact, have not put a photomultiplier here at all, and had this light bouncing off some other surfaces and doing something else before it reaches some other photomultiplier there. That looks much more complicated. We didn't analyze it. But we would have to take this, it's reflected from here, it goes to here, it's reflected from here, and comes to there. It's one of the alternatives. Of course, another alternative might be, I'm not talking about the different alternatives now, another alternative might be it comes to this surface, it goes up here, and it hits that one and gets reflected to the photomultiplier. The orange one is just a different alternative. The alternatives we add. But to calculate for one alternative, one of the alternatives, namely, say, the brown one here, I can think of this as a series of steps. Even when I got here, you remember I had an arrow. When it was a photomultiplier here, I just took the square of the length. But if there's some more equipment here and things have to go on, I can do more to the arrow to carry it further till I get to there. Okay? I could do more things. If I know what was coming up here as a net arrow, I can take that arrow and do more if it's going to be reflected. I can use that as a source, in other words. So the way we do it in succession is by a process of composition, which we call multiplying, and I'd like to describe the ideas of that. So I would like to say that a particular way can be analyzed as a succession of events. So if there's a succession of events, let's see, get the corresponding color, succession of events, you divide the total way into part ways, so to speak, a succession of ways. Succession of partial operations, or say events. It's not really events, it's things that happen. Succession of circumstances.
Transformation.
It just means a succession of things that can happen. That's what it means, that's what I'll say. Things that can happen.
Things is a marvelous word.
Yeah, it's a substitute for a blank. If it's a succession of things that can happen, what do we do to get the net amplitude? The answer is, it's equal to what we call the product, or the multiplied of amplitudes. Now that's a new one. What does that mean? Amplitudes, remember, are arrows. How do you multiply arrows, and what do you mean? I have to define it. I define adding by saying arrows look like steps, and what we do is we add for the successive steps. I want you to notice another way that one can think of arrows. Since this we've had this general, as important as it is, I'm erasing it. Huh? Can't help it. I want you to think of an arrow in another way, which is rather interesting. Here is an arrow, just like one of these. Now for multiplying, you have to think a different way than for adding. There's an arrow. Now, let's say it's a fifth long or whatever. I imagine there's a standard arrow, and the standard arrow is always a side horizontal and has a unit length. That's a standard unit arrow. Now suppose I have a second arrow and I want to multiply them. Here's another one. I'm not going to draw it on the top because I don't want the diagram gets complicated, okay? Here's a second arrow. Well, let's say, make it more interesting. It goes this way. All right? By the way, it also has a standard to it. There's a standard one here. But that's not, that won't be important to it. The question is, what do I mean by multiply? I mean the following. Oh, I described the arrow first. I'm sorry, I shouldn't have written this yet. Let me first describe this arrow in another way. The first way was to say it's a step. The second way is to compare it to the standard arrow and ask for the relation. And consider this as a relation. It's been turned. How do you get to this one from this one? You can turn this one and shrink it. So an arrow describes, from this point of view, it's equivalent to or describes not a step now. It does that too, but we're doing it for a different purpose. We're looking at it as describing a rotation and shrink scale. Namely, how much I have to rotate the standard and how much I have to shrink it to get the arrow I want. Right? Now, multiplication of arrows means that you do these rotations and shrinkings in succession. For example, to get this arrow, I have to rotate and shrink. If I take this arrow, and if I rotate this arrow by that rotation and that shrink, I've multiplied them. In other words, consider this arrow as a rotation and a shrink, and this is another rotation, but this is also a rotation, a big one, and a shrink. If you were to make first the one rotation, then the shrink, and then the next rotation, the shrink, the net result would be some little arrow somewhere. I can't quite see for a moment where it is, but that would be the result. The easy way to see where it is that it's here. Let me see. This is that. It's here. This red is the product. And I'll explain what it is. It bears the same geometric relationship to the purple arrow as the blue one bears to the black one. In other words, it's supposed to be turned the same degree and shrunk the same degree as this blue is relative to the black. That is, this is to that as this is to that. That's the way multiplication works, you know, with numbers, it's the same. If we were to, that's why we call it multiplication. Let me show you why it's similar to multiplication. Suppose you wanted to say that 6 is equal to 3 times 2, which is true. But let me look at it a different way. The 2, purple, 3 is purple, and 6 is red. How's that? That's going to be nifty. I love this color business. I never used it very much. The only problem with it is to remember what color to make everything. This is the analog. I'm going to show you that's the analog. And I'm going to think of it this way. That 2 bears a relation. 2 is not a number from this point of view. It's a relationship. It bears a relation to 1. It's an expansion of 1. How much do you have to expand 1? You have double. And so if you want to write 2 times 3, you take the arrow 3 and do the same thing to it that 2 was relative to 1. In other words, you think of 2 relative to 1. There's a 2 and a 1, and you think of the relationship between them. It's doubling. That's what you do to 3 to get 6. That's why it's called multiplication, because we do to this arrow what we had to do to the original one to get the blue one. And if we do that, we call that multiplying the 2 arrows, okay?
Aha, aha. Okay.
Actually, it'll turn out that the length is simply the succession of shrinks, which is simply the multiplication of the lengths. The length actually multiplies.
I missed where,
And just a moment, please, just a moment.
I mean, what you-
Just a moment, please. And the angle is the sum of the two angles. In other words, the extra angle is the original angle. So another way of saying what the answer is the final position is the sum of the two rotations. The rotation is the sum of the two rotations, and the size is the succession of the two shrinks, or the product of the two shrinks. Yes, sir.
your product then is the upper blue and the lower, what's that, purple?
No, I'm multiplying blue by purple to get red.
Right. okay.
Yes, right, okay, good. And it's really quite easy at the end. It's just that the rotation is the sum of the rotations, and the size is a succession of shrinkages. All right? So if you have 5 of them to do, instead of going crazy with this geometry again and again 5 times, you can just tell you what the answer will be. The length of the final arrow will be the succession of the shrinkages. If you shrunk it 1/5 the first time and 1/3 the second time and 1/2 the third time, it'll be a 1/5 times a third times a half, which is a 30th. So that's the side. And the angle will be the sum of the angles. If the first one's at 15 degrees and the second one is 27 degrees and the next one is at 16 degrees, then the sum will be equal to 58 degrees. Boy, that was fast. It was also right. Okay. So the angle is the sum of the angles in a multiplication, and the shrinkage is the result of the successive shrinkages. And now we can understand how we compounded that. We could compound that first arrow when we came from here to here to here. It was really quite elementary because we did an elementary example, but we rotated a certain amount, we shrunk it, and then we rotated some more. Net result, total rotation is the total distance, and size is the total amount of all the shrinks. There was only one shrink. Let me do an example where there are 2 shrinks so that we can see a little more interesting case. These were too easy. I took the easiest cases first. All right?
Got it.
Got it. Then I can erase this stuff, huh?
Yep.
Yeah. Because I need a lot of room to draw a picture. So let me take an example of another problem. Actually, it looks the same. I'm going to talk about a different situation on this same apparatus. It's kind of fun. Again, to your exhaustion and boredom, I draw the glass plate. Yes, sir. And here's the source. Well, you always find it'll be interesting. I always tell you something interesting, so be patient. Here's the source, and here was where we put the photomultiplier before. And after fiddling around with, as a function of the thickness, we got a result which we plotted, which was the probability of reflection as a function of thickness. We don't do that with one experiment. This represents the result of a succession of different experiments using different glass plates of different thicknesses. Some reflect strongly and some weakly in the way advertised, this being 16%. Now, instead of the photomultiplier being put there, we're going to put the photomultiplier on the other side, down here, to see what we get here. That's the wrong color, but so I put the black cap on the blue ink. Horrifying. That's the kind of thing that just drives you nuts. It doesn't make any difference what color anything is. Now here, I put the photomultiplier there, and then I tried to find out what the result ought to be. Okay? So we have to learn some lessons. First, suppose we had a single surface. It's hard to put the photomultiplier there, but never mind. Suppose we had a single surface. What happens at a single surface? So first, we get the rules for a single surface. For a single surface, I told you that when it was reflected, the arrow is shrunk for reflection. Shrink 20 to 20%, or 1/5, and reverse the direction. That's 100. That's another rotation. Direction if air to glass. Otherwise, don't shift the direction. From glass to air, you don't. What about transmission? What do I do for the amplitude to come through? So I call that transmission. I say the answer to that one, I'll tell you, is shrink to 98%. All right? So well, there's a new rule. I'll tell you how you can remember that 98 if you know the other one. Because the chance of finding the photon over here is the square of 20%. Remember what that was? That was a 4% chance of finding it here. 4% was the chance that this photomultiplier would find it. But we don't lose any light. We don't lose the photon. Nowhere can it go but either there or there. So the chance of arriving here, better check out right. Let's see if it does. If it were shrunk to 98%, this arrow is 98 long. The one that comes out over here. It's 98% of 1 instead of 1/20th. And the square of 98 has been carefully prepared. So within the accuracy of the arithmetic I'm doing, if you multiply those together, it comes out very close to 96. If it doesn't come out exactly 96, then the 98 has to be adjusted slightly. Because it's 96% is the chance of arriving here and 4% is the chance of arriving there, so the 100% of the light is accounted for. That's why this number is related to that number. Okay? All right, good. Now what I want to do with that rule is to find out how much light comes here. All right? So let's go. So learning the rules about arrows, we start. We think about the light that comes down this way. It's this surface and then continues. That's one way. It's rotated by the total distance from here to here plus the distance from here to here. 1,000,000 rotations plus 6.1 degrees. All right? Result is we get an arrow for that, which is off at a particular tilt and has a nice long length of 98. Why 98? Because it went through a surface. Now there's another way it could happen. It went through this surface. I'll draw the alternate to one side so you can see it. It's on top, okay? I'll even draw a dotted line for the second alternative. The second alternative is to cut down to the photomultiplier that way. This time it's reflected from the second surface. What would the result of that be? Well, because it's reflected from if it can go transmitted by the second surface. It's transmitted by a surface, it's 98. And the angle is the total time to go from here to here. Ah, somebody is awake. Exactly. So the second arrow is another arrow, 98 long,
Half rotation.
with the same rotation.
You need a half one because of the front surface.
What?
You need a half rotation because of the front surface.
No, it's no rule about changing the direction and reversing things when it's a back surface. You don't reverse. For reflection you reverse, but not for transmission. Now what's bothering me is I'm getting 2, of course. But I really counted the same thing twice. Slightly disturbing. And at 1, and I should get a shrink.
Get another shrink there.
That's what I should do, yes. I should say it doesn't go through without shrinking. That was a mistake. I made an error. I made an error.
In the previous one, we were back.
That was a mistake, excuse me. It goes through, but it has to go through again. Okay, that's it. That's the double example. So what has to happen is it shrunk by 98 when it gets to here, and it shrunk by another 98% when it gets to there. And the rule of succession says that the angle is the total angle for all the pieces put together, which is the total distance. And the size is a succession of shrinkages. That's what I was trying to illustrate, and I did it wrong. Therefore, it's 98 times 98, or 96, right? Because 98 times 98, I told you, was 96. So the length of the arrow now comes out 96. That is to say it was shrink once, and then shrink again. You shrink it 2%, you shrink it another 2%, it's pretty close to 98. I leave it, it's not exactly accurate, the numbers, but to 4 decimals, it's not right, but to 2 decimals, it's right. So its length is 96. And it's easy to find out what the intensity here is. The intensity then would be 96 squared, the probability, I mean, to arrive. The probability is this area of the circle, of the square on here. You might get confused. It looks like I've already squared it. No, I found the arrow by 2 successive shrinkages. Now I have to do the rule of converting arrow to probability by making the square. So now I'm getting the probability, and I'm saying that's the square area corresponding to a line is 96% of a unit. And if you square that out, it's very reasonably close to 92. And therefore, we've calculated that if I were to plot the transmitted light on a graph here, in fact, I'll use the same piece of paper, and I'll plot the transmitted light, and that's way up here at 92. And we've just wonderfully deduced that it's independent of the thickness of the sheet, and everything's wonderful, right? Or is there a problem? Because if the 92% of the light goes through and 16% is reflected, we have a kind of a puzzle which even the quantum mechanical logic can't straighten out. Something's wrong. What's wrong is that we haven't made this calculation complete enough, or calculated accurately enough, and I would like to show you why, right? Why is because there's still another way that it could do it, that we have to add to this 96. There's another alternative. I see we have only one alternative here, but there's another alternative, which now I will draw up, as I was supposed to last time, the colors of the caps. And the other alternative will be drawn in blue. You start here, you shrink, you come here, you reflect. You come here, you reflect. Then you come here and you shrink, and you go down. It should be in the same place, of course. I'm just drawing to one side.
If you take that reflected
Yes.
as another alternative,
Yes.
how many of those would you end up having to do? It seems it would.
I have to do them all. You do.
Could it be infinite?
It is. Have patience. Let's do the first one.
No, I
and I'll
understand.
discuss the second one.
I was just wondering how many of those we're going to do.
All of them.
Well done.
Yes, yes. We're not.
Coffee breaks.
You'll have a coffee break in a minute. We've got 50 minutes yet, so you'll have to bear with me. I'm going to do 600 of these in the next 15 minutes. However, in order to start, we have to do the first one. We'll never get to the 600th unless you do the first one, so let me do the first one. Yes, I am actually doing, thank God. It's good we have you here to correct me all the time. We're doing the second one. Now let me say how we do that one. All right? Let's consider the size of it first. It's going to be a succession of events. It goes from here to here, 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 it goes from here to here. There's 5 or 6 events there, right? I mean, more. It goes from here to here, then it's shrunk through the surface, on account of the surface, then it goes from here to here, then it's shrunk because it's reflecting, then it goes from here, then it's shrunk because it's reflecting, and it goes to here to here, turning, and then it's shrunk again, and oh boy, right? But you remember the rules of multiplication are very easy. To get the total angle, you just take all the rotations. Let's count them. It's the time to get to here, plus, because we add the rotation angles, the time to get to here, plus the rotation for here, plus the rotation for here, plus the rotation here. Simply the total time. Okay?
With 2 reversals.
And 2 reversals? Nah, unfortunately, it would be fun if there were 2 additional reversals. It wouldn't be very exciting because 2 reversals brings it back to where it was, so we don't have to worry whether we reverse it or not. That's why I can't tell from this one.
But it's back like it's.
But either way, it doesn't make any difference. 2 reversals is nothing, and 2 non-reversals are also nothing. Actually, I think it's non-reversals. But either way, I get the same answer. Okay, no reversals we have to worry about, right? Because they're 2. It's nice about reversals. Okay, now let's see what the shrinkages are. 98%, 20%, another 20%, and 98%. In other words, total length at the end is 98 for the first shrink, 20 for the next shrink, 20 for the next shrink, and 98. I get these numbers because the first one is a transmission, the second one is a reflection, the next one is a reflection, and then is a transmission. That's the rules for reflections and transmissions for the shrinkages. In a calculation like this, 98, the accuracy I got, 98 is practically 1, and I'm going to be sloppy, perpetually sloppy. All this can be done more accurately, of course, all right? But I'm illustrating. I'm not doing the arithmetic very accurately, but I'm illustrating the main points. So that this is, I call this 1, I call this 1, I can forget them. And this times this is about 0.04. Again, remember, we're not finding the area of anything, we're finding an arrow size. So the blue arrow that should be added to this black one has a size only 0.4. All right? That's the size of the arrow that has to be added. Before I add it, it should be drawn from the same center if I were consistent, Claudette. It should be from here. And I would like to take away that square now so we know how do we square them, right? It should be from here. But the question now comes as to what angle it's at. Well, what is the angle? Is it big, the same as this? Is this time the same? No, because you have 2 extra passages through here, right? So that it's a different angle. Corresponding to twice the thickness. Let me draw that angle out here. Perhaps it came out this way. I drew it a little, it's 0.04, and it's tilted at some angle that depends upon the thickness. Right? So what are the possibilities? Suppose the thickness was very small. Then that angle would be nothing. These 2 things would add together. Right? They would be in the same direction. If the thickness was very, now I'm going to do cases, okay? One case, that this is very small. Then the difference, the extra distance, the double thickness, so to speak, is nothing. And this arrow is in the same direction as this arrow. Can you see anybody excited or delighted? 96 plus 04 is 1. The probability coming through is 100%, which it must be, because the probability of being reflected was 0. Now, suppose we go to this place here. What was that? That was when the other case was opposite. Let's hope, and I'll explain why the hope is in fact correct, that at that distance, that thickness, I went blue and black are all mixed up because the caps are driving me nuts. I wonder if black could be under the blue cap. It's a reasonable hypothesis. Ha! Black is under the blue cap. Everything's going to be straightened out real fast. There's the 96 again. I just draw it to one side because I don't want to draw everything on top of itself. Now I add the 04, but this time I have it rotated the worst possible case. It's this way. So there's the 04, and the other one was 96. And therefore the total net result is this little arrow. Here, that's the net total result. That's only 92. Right? 4 minus from 96. And the probability then for that case is 92 squared, this area, and it comes out 84 approximately.
Fantastic. You lucked out.
I lucked out, and that checks with the 16 here. The only thing I have to verify is that I really have the right angle at the right place. But you remember, in order to get that, I also had to have a pair of arrows which were previously opposite to be lined up exactly, 180. Here I said that things that were previously parallel are opposite. Are the angles in this case the same as the angles in there? Just think, yes. Because what is the angle difference? The difference in time of coming down to the first surface or going down to the second. Notice that going down to the second means 2 extra passages through the material. Exactly that this extra one is 2 extra passages through the material. It's the same change in angle, so everything's fitting perfectly, okay? And this is, by the way, a rather miraculous thing, that these arrows always add up to 100%. It's crazy that these rules do this, and in fact, theorists in more complicated problems sometimes use partial knowledge to get other knowledge by using this principle that it always must add up to 100%. It's called the principle that the theory must be unitary, but never mind the words. It just means everything has to add up to 100%. That's why I could check this 98, get this 98 right. And also, well, in this case, I couldn't find the direction shift by that argument, but anyway.
At this point,
Yes.
it'd be nice to see that the first multiple reflection that ended up in going out back to the photomultiplier didn't have much effect.
All right, now we have to do something. He wanted us to do it 1 million of these.
I did.
600 of them. And I promised to do it, so I have to do them now. So if you'll excuse me, instead of doing what you asked, I'll just do this case more. It's the same kind of a thing. Therefore, let us consider the next one, which I will draw in red, which would be in your sequence of millions and millions of terms, which are all there. Another term, which is that it comes down to here, goes through, is reflected again, decides to get reflected again, and finally goes through. Okay? Okay? What happens here? Shrunk by 98, shrunk by 20%, shrunk by 20%, shrunk by 20%, shrunk by 20%, shrunk by 98. Therefore, the size of this one is, writing in red for the red case, 98 by 20 by 20 by 20 by 20 by 98. Again, estimating that the 98 is nearly 1. We have an arrow which we shrunk by a factor of 5, 4 times in succession. The first time we shrunk it twice, and that was 1/25. That's 4%. We shrink it 2 more times, it's 1/25 of 1/25, which, as it turns out, is 1 part in 625. It's a very tiny arrow. It's very small, so I left it out. If you want me, I'll put it on this diagram more carefully. But it'll be hard to be able to see which direction it is and how big it is. Because it's 1/25 as big as the blue arrow in size, and it's at some crazy tilt. Now, you'll notice that when I did my arithmetic, I left out, I only calculated the 2 places and so on. If I calculated absolutely accurately, those things wouldn't check out so perfectly that I had 100% exactly. But then I would, when I calculated all these other terms, they would.
Because these terms would be extremely small.
They would be small, but they're important for, if I would calculate the 4 decimal places, everything, I'd have to include these before I could demonstrate that it came out exactly 100% the 4 decimal places. I can prove it the 2 decimal places with only 1 term. But there are, in reality, the infinite number of terms. All right? It likewise for the reflection is an infinite number of terms.
Okay, in that example, there'd be, the arrows wouldn't be reversed because in effect there's 4 reversals.
Yes, again. But in the other case, we want to do one of the other ones with reflections. With reflections, we had a 20%, and then the other one was that we interfered against was this arrow with 20%. But the new arrows would be things that would go like this, boop, boop, boop. Okay? Now we know how to calculate those. I'm not going to make, you see, I never did make the correction of this going through corrected by 98. That should have been. And some of this adds on to undo that. So that I got it right, huh? Anyway, we're coming this way. Let's look at the 20%. The 98s are small potatoes relatively. Got 1, 2, 3 instead of 1. And that means they're 25th the size because there's 2 extra shrinkages. And you can get the sign right by thinking that in this particular case there's 1, 2, well, every reflection in this case is from the back, from glass to air, and there's no reversals. Right? The reversals are from air to glass.
On the first, okay.
Whatever the rule is, you follow the rule. We're just not going to actually do these things. We just want to understand what's involved. Yes, you have to calculate all these terms. As a matter of fact, I must say that in many problems, in practice, when there are complicated problems of scattering of electrons and various things, we try to identify what's called the major or most important contribution to the amplitude and compute that. And then if there are subsidiary contributions to the amplitude that are smaller, such as these, in a real problem, they must be much more complicated to calculate than they may be. Here it's not much more complicated. To multiply 2 more 20s was easy. But if this is a more complicated circumstance, the higher contributions can be very much harder to calculate, but they're also small. So what happens in practice is we calculate this, and then we use a computer for that, and then we use a computer over several weeks after somebody invents a better technique to get the next term, and we die exhausted and get the answer to 1 part in 10 to the 10th for some problem. And that's just about the accuracy of experiment. When an experiment improves, then they go crazy. The technique for calculating improves, and they're able to get another term. And so far, this race has always checked. The experiments sometimes ahead, the theory sometimes ahead, but they always agree. I mean, the calculations. The theories never changed. The theory was you're supposed to add them all. But you can't do it in practice. It's too much work. You do more and more work with better computers and so on and improve the calculation. At the same time, you do better experiments and improve the experiments, and they're chasing each other. So far, it's always been working. Okay? In other words, when the calculation claims to have a certain accuracy and the experiment claims to have a certain accuracy, then the results agree within that accuracy. Okay? Good? So now we know the rules for succession and the rules for alternatives. And that's all we need to know. That's the whole mathematical structure of the composition of amplitudes. And now, the next step is now physics. Well, I'll explain the idea, but I would rather do it while I'm not erasing the board because it's a kind of an interesting thought. We have a way of decomposing a process into alternatives, and any particular alternative into a succession of, so to speak, smaller and simpler events. Can we decompose nature into such simpler events? And how simple are the fundamental events? And how many different kinds of fundamental events are there? Do you understand what I mean? Suppose we said the only thing light ever does is get reflected from surfaces and go through space. And for going through space, you rotate at a certain rate, and reflecting from surfaces is some other rules. That would be okay, but it's not really true that it only reflects from surfaces. It can also bounce off of other things, gas molecules, et cetera, so it's more complicated. But the question is, can we, when we look at nature, resolve it into some kind of elementary operations so that what looks, if we looked at in the great detail at the elementary operations, very large number of them may be involved, and the calculation of the amplitude may be complicated. We're not worried about technical complication. We're worried about a matter of principle. How complicated are the fundamental processes? And how many are there? And if I were to write down the following, could I write down a list of fundamental processes which can occur in nature, and the rule to making the arrow of each? Then add these two general rules of how to put them together. If the process is a composition, you multiply the arrows. If it's alternatives, you add the arrows. But all I have to know are what the alternatives are, or what the tiny pieces are. And the answer is, for all the phenomena of what we call quantum electrodynamics, which includes electricity and magnetism and atomic behavior and light and mechanics and everything else, there are almost, it's true, that there are only three rules, three fundamental processes. I said almost because I've just realized something. I've left out an aspect of light, which is its polarization, and I want to continue to leave it out because the principles are always the same. It's just a little extra complication, and it's rather minor. And we have a limited time, so I'm leaving that one out. It's a minor, interesting, but minor complication. That there's really two kinds of light, polarized one way and polarized the other way. If there were only one kind, everything I said was right. In the same way, electrons have a kind of polarization, and I'm going to leave that out also. Leaving that out, of course, frightens you. When I leave something, I say, that must be where it's complicated. No, it isn't. I'm telling you the complicated part. What I'm leaving out is relatively simple. The three fundamental processes will be described in just a moment. Well, I'll tell you what they are. First of all, we have to look at things differently, much more detailed than we've done before. And we're going to look at them not only in space, but in time. We're going to ask a question like this. What is the amplitude that a photon liberated at this point at a given moment arrives here at a different moment? You say, what color photon? Now you don't have to say. That's what John, who was here all this time waiting for, has been trying to say. That the color of a photon is something else which we have to explain. What we're going to talk about is the amplitude, if it's liberated at a given moment from a source, to arrive at a given moment at some other point in space. That's a certain formula. It depends on the distance and the time delay. That's one rule. Second rule is an electron. It's another particle we haven't talked about. Liberated at a certain point, has a certain amplitude to arrive at some other point in space at a given time. There's two rules. I haven't told you the rules, but I have to give you the rule. And the third rule is this, that the only thing that can liberate a photon at the level at which we're working, it's true that mu mesons can and other particles, but let's keep the system simple with just electrons and photons. Only way a photon can be liberated, a photon never goes, bounces. I kept saying it bounces from the surface. We have to correct all that. We have to look at it in more detail, see what really happens. Photons only get absorbed by electrons or get emitted by electrons. And the way we can represent it is this way. Say an electron is, this is supposed to be space. An electron's going along somewhere, and it emits a photon and goes off some other direction. Another electron can come along and pick up that photon and go in the other direction. In other words, electrons can emit or absorb, and by the way, with the same rule, a photon. And then we have to have an amplitude for that, for emission or absorption of a photon. So we have three rules for amplitudes. The amplitude of the photon goes from one place in space and time to another. The amplitude of an electron goes from one place and time to another place and time without any disturbance if it didn't do anything. And the amplitude that an electron emits a photon. And with those three pieces, we could compose all kinds of processes. As a matter of fact, I've already composed one. The scattering of an electron by electron. Electrons interact, we say, by electric fields or something. They bounce and they push each other. The picture that we have in the quantum mechanics is not a bounce and push each other. What happens is an electron goes along, emits a photon, which the other one absorbs. And there's an amplitude for this process, which we're going to calculate by putting together pieces. The pieces would be composed of the amplitude for the electron to go from here to here, times the amplitude to go from here to here. The amplitude for the electron to go from here to here, another electron, and the amplitude for it to go from here to here, all multiplied. Multiplied the way we've been talking about, adding angles and shrinking in succession. It's still multiplied by the amplitude of the photon to go from there to there, and two more factors, the amplitude that it emits a, electron emits a photon, and the amplitude that it absorbs a photon. So that is a way, by putting together a Tinker Toy set which has three parts. The amplitude of the photon goes from one place to the other is one part. The amplitude of the electron goes from one place, and time, I should say, to another is a second part, and the third part is the amplitude an electron emits a photon, which is the same as the amplitude that a photon absorbs. The emission absorption is the same. And with those three parts, all of the, almost, of the part of nature that we're talking about is to be described. And just like in our simple example, we found out how mirrors and lenses and so forth worked in the normal fashion, strange as it may seem when I give these amplitudes, there's no hint in these forms of anything simple about simple, why does anything simple happen? Nevertheless, when calculating and adding all the arrows and doing everything, you get all the simple phenomena out of that. You have a question?
You would then see Compton scattering as the absorption and then the emission of the photon.
Compton scattering is a special process in which there's a photon coming along. Any scattering, a scattering from an atom. We talked about a photon bouncing out from something previously, being reflected from a surface. That was cheating. That wasn't right. That was an approximation on the step to understanding, okay? A deeper understanding of what happens is that the photon that comes out is different than the photon that went in. That what happens is a photon goes in, an electron picks it up, then the electron moves around somehow, and then a photon comes out. So what we called about reflection was going into the glass, disappearing, and then another one coming out of the glass to the detector.
Are those free electrons?
In the glass, it isn't. In the glass, there's also charges in a nucleus. I haven't spoken about that. In order to include the nuclei, we have rules with quarks and so on, which are complicated. But nuclei in practice, in most circumstances, are so quiet and so dead that the rules for their amplitudes can be approximated. They just sit still, and they emit photons too, which go between the electron and the nucleus. And that's what holds the electron to the nucleus, these photon exchanges. So if it's not a free electron, it's a very much more complicated picture. It could be a free electron, in this case it's called Compton scattering. It's just a technical word because it was discovered in cloud chambers. But an ordinary electron in an atom is in perpetually, have photons going back and forth, an amplitude for that to happen all the time, and it keeps its motion around the nucleus on account of that. And a new photon coming in can hit it and disturb it and do something, but then ultimately a new photon will come out, and that's the scattering of light, all right? A new photon.
Then if you have an electrostatic circle actually charge between two plates, then you can explain the exchange of photons.
Yes. It's much easier to do with an electric field, because in lots of circumstances, what many of the photons are doing are the same as what other photons are doing, so you can simplify the mathematics a lot and then talk about things like electric fields and so on. Just like we saw with a mirror. In certain practical circumstances, we make believe it's a ray which just goes from one point to the other. But in deep down, fundamental detail, yes, all interactions would simply be photons rushing back and forth between these things. Those photons would be ones who have a wavelength longer than the size of the capacitor. And so they do funny things that you don't expect. It's not like a real photon because they're only in there temporary and you can't make up your mind whether they're there or not. Remember, we learn all that. If you don't observe it directly, you can't tell whether it's there or not. In other words, let's say, here's a scattering of an electron. The fellow who wanted us to do 600 terms would be immediately insisting that there's another one, another possibility. Maybe the electron looks the same on the outside. That is, it's coming this way in a certain condition, starts from a point 1 and a point 2 and goes from 3 to 4. And here we start from a point 1 to 2 and go from 3 to 4. The same places. I mean, I've drawn them on another place in the blackboard so you can see it. But we're trying to represent another way it could happen. It might have exchanged 2 photons. I drew it like that. Not that they cross is any important. It could have been that they didn't cross. The arrow, or the amplitude corresponding to this possibility, must be added to the amplitude for this possibility before we get the probability. And under those circumstances, we can't say how many were really exchanged. We can't say either one is exchanged or 2 are exchanged in the normal sense of probability. We have to say there's an amplitude for 2 exchanges and an amplitude for 1 exchange, and you've got to be careful between the difference of saying there are alternatives which have amplitudes and there are alternatives which have probabilities. We can't tell you the probability that this happens. Doesn't mean a damn thing because this might happen. And what happens in the nature for this experiment is a sum of amplitudes for these, and in the usual business we can't talk about what we don't observe or we get into trouble, okay? So in the case of the capacitance or charges on plates and so on, it looks very strange to say all these photons are there because you don't see any of them. The actual number is indefinite. It's a sum of contributions from 1, 2, 3, 4, and so on. And you can't say how many there are, and it's very different. But it's very quantum mechanical. And most peculiar is that weird business of making arrows and so on all the time when you don't need them, right? Gives the same result as simple-minded views in many circumstances. But the miracle is that the arrows, which agree with the simple-minded views, also agree with experiments and circumstances where the simple-minded views collapse. So it's a more general and satisfactory theory. It's the base of all of the rest of the theories. It always tells you by looking at the arrows where you begin to make mistakes if you keep on using the simple view in more delicate circumstances. It's the fundamental theory. And it's nice that the fundamental theory has just few fundamental parts. Okay? Now, I have inadvertently said something when I did that. I advertently or inadvertently, whatever. I've said something, I've implied something when I said that, which I would like to emphasize. And that is an interesting circumstance. Suppose there were no photon exchange. That must also be added. And then we would add the amp for that case, which is drawn up here, if it's at all possible from the geometry of the circumstance, whatever it was. We would have an electron, the same circumstance again, but redrawn on another piece of paper, okay? Starts at 1, finds an electron at 2, there was 1 at 3, and 1 at 4. Another possibility is they went directly. In some of our experiments, we had to get rid of the direct one. Remember, even with the reflecting layer, there was a way that the photon might have snuck around into the counter directly from the source, but we put blocks of stuff in between. If we haven't bothered to do all that, we have just a direct thing to do this. And now I notice I said something, that the amplitude for this is the product of the amplitude. This electron goes from here to here, and that electron goes from there to there. I just said that when I said this. I implied that. And what I want to say is that the rule for the product has two cases, two aspects. One, things happen in succession, beep to beep to beep to beep. Or things are happening sort of somewhere else simultaneously. The simplest example is this. Here's an example of a product. We want to know if this electron can get to here and that one can get to there. The amplitude that two things are happening concomitantly, which are not interacting or not doing anything, is again a product. The product is used in two cases. When successive things happen or when two things have to happen. All right? Either because they have to happen in succession or because they have to happen simultaneously. It doesn't make any difference. You multiply the amplitudes together. I will emphasize that still a little bit further because it makes a very big difference. It's where most people who learn quantum mechanics in schools and stuff have the biggest trouble. Because they don't learn, you see, just like we did. In all of the simple examples, we only had one photon. So our amplitudes always were the amplitude to find a photon somewhere. All of a sudden, we're talking about the amplitude that two things are happening. It would correspond to the amplitude for two photons to do something. It turns out that if you're always dealing with amplitudes for one object, it's close enough to the old wave theories that you can keep on going with the wave theory and just at the last moment say, well, really what I was calculating was a probability. And use old ideas. There's a certain stiffness, you know, with old ideas. You like to lose what you learn. And so there's a tendency to try to do that. But the moment we talk about two photons, amplitude for two photons, all the wave ideas and so on prove quite inadequate. Now I'll give you an example of a two-photon process that we're going to calculate the probability for instead of a one-photon process, all right? Ordinary, up to now, we had one photon, might have gone this way, that way, there's an amplitude for each way. Now I have a problem with two photons, and here's an example. It was discovered, well, here's an example. We have two detectors, because we're going to detect two photons. These are the photomultipliers. Two of them. And we have two sources, A and B, which you might imagine even were stars far away or anything, but different sources.
Same wavelength?
We'll make it the same wavelength by building these detectors, putting filters or something in front of the detector so they only detect one wavelength. Or make the sources exactly the same wavelength. Since I mentioned stars, however, I find it difficult experimentally to go up on the star and put a filter around it, so I'd rather put the filter around the...
Two streetlights.
Two of the yellow sodium lights, yes. Actually, not really street lights, because although it's monochromatic nearly, it's not perfect. And by the time you get the street lights as far apart as they really are, the 100 feet, the lack of monochromatic is so bad that you can't find interferences between two lights. They would have to be extremely close together and very carefully made. But you can easily do this experiment, very easily, with two lasers set a few inches apart in a laboratory and put two photomultipliers off to a few inches apart. In fact, more than a few inches. Okay? It's questions of conditions and dimensions. But anyway, here's the problem. What is the chance that both photomultipliers go off together? So what the event that we're calculating the probability for is not that one photomultiplier goes off, but that there's a coincidence of two photomultipliers going off. So we have to ask for the probability the two photomultipliers going off. Probability, that's the event, which we want to study the probability of, is two photons, or two photomultipliers, I should more accurately say, photomultipliers, go off together. Together is within a certain accuracy that depends on the technique and the experiment and so on. We'll say the same time for the purpose. There was some delay in the photomultipliers.
1 nanosecond.
Yes, actually, that's a pretty good time to do this. Now that's the event, and so what we have to have is an amplitude for that event. That probability, as all probabilities, is equal to the square of an amplitude. And therefore we're drawing an arrow now for an event which involves two photons. Do not get the idea that the arrow is attached somehow to the photon. And if there are two photons, there are two arrows. That's wrong. And there are 2 photons, there's only 1 arrow. The amplitude that these 2 photons are doing what they're supposed to do. Oh, there may be more arrows in your analysis, just like when we had 1 photon coming from different surfaces, we had lots of arrows that we were talking about that I drew that were added together and multiplied. But the idea is we're computing the net result 1 arrow, and maybe use arrows and stuff to compound it, but the result is 1 arrow. There's 1 arrow that gives the amplitude for a complete event with 2 photons, not 2 arrows. Okay? Actually, it is you can work it out in terms of 2 arrows, but they're compounded by multiplication to get the final arrow. Let me show you what we have in this case. The things that can happen is possible is that both photons came from A and B didn't do anything. That can be distinguished from the other. That event is not completely described. I can, by looking at A and by looking at B, later determine whether it was A that let out both or that B let out both. It's not easy if there were stars, and you have to add possibilities. But let's suppose that we have some way determined that one from A and another from B. By the way, that raises a question which I ought to describe is when you can separate cases and when you can't, but let's disregard that for just a moment. Let's suppose we have some way to know that this one only emitted 1 photon and that only emitted 1 photon. Just make it easier for a moment.
Can't you just put a wall between the two?
Well, there's a wall between the two. That there is. I don't want to worry about that, but I don't, the problem is, how do I know that the 2 photons didn't come from A?
No, put your wall all the way down.
No, I don't want to do that. That's not an interesting experiment. Okay, now, how these 2 things can go off? It could be that A sent its photon to counter 1. Let's say this is counter 1. This is counter 2. So the first, well, I'd rather use 1 and 2 for something else. Let's say this is counter little a, this is counter little b. There's one way the event could happen. That big A makes little a photomultiplier go, and big B makes little b photomultiplier go. Let's calculate that amplitude first. That's one way. There are alternative ways. Perhaps it would be a good idea to list the alternatives before we make any calculations. That's one alternative, the blue alternatives. I love these colors. Now the red alternative, which is another alternative, and we must sum the amplitudes for each alternative. Huh? So we're going to compute each one separately and add them together. The other alternative is that it's A that sent its photon that made the little b counter go off. And the cap A source made the small a photomultiplier go off. That's a different alternative. And the correct way to compute this in the quantum mechanics is then to compute the arrow corresponding to the blue alternative. So we would get the amplitude for the blue alternative, or the blue amplitude, the blue alternative, and the amplitude for the red alternative. Now what we're going to, does anybody know what we're going to do with these 2 amplitudes? When we're finished, to get the total and the net amplitude for the whole process. We add them because these are alternate possibilities. And when there are alternate possibilities, you add the amplitudes. They're not successive possibilities. It's not that we're asking that it crossed and then went straight or anything. That, if we did that, then we would multiply them. Okay? So now we know what we do with the 2 alternatives. We're going to add those alternatives. But what do we do with each one? Now we have to just compute the blue alternative. Forget the red lines then. We'll come back and do the red one later. How do we do that? Well, let's say that there's some kind of an arrow that represents the amplitude that this capital A counter makes little a go off, and I'll draw some arrow to represent that. At some crazy tilt that the details of this layout hasn't permitted us to calculate. It's 1,265,642.18 rotations. You see the 0.18. All right? That's the result. That's the result, which I'm going to call A to A. Now, what would the arrow be for capital B to little b? Well, it depends on, did I really have these exactly the same spacing as these? Is it all symmetrical? Let's suppose it is. It doesn't have to be. If it isn't exactly the same. But if it was a symmetrical case, then the same arrow, which I will try to draw on top of itself, would represent B to B, both together. Right? Let's say the length, for simplicity of analysis, let's say the length of this is 0.4. unusually good detector. 0.4. Any number. What's the total amplitude for the blue alternative? Now comes the rule you want of multiply. These two things are happening independently and simultaneously, and so we multiply. So the amplitude for the blue alternative is to multiply these, is the product of these, and therefore is equal, if it's the blue alternative, why am I writing in red? The product of these and is therefore equal to an arrow. This is the net result for the blue alternative. There it is. You see that arrow? How long is it? It's 0.16. And what angle is it? It's the sum of those two angles. Both angles are the same, so it's the double of that angle. I meant to draw this at an angle inclination which is twice as great as that one. I hope it was approximately right. All right? So the arrow for the blue alternative is here. We've got it. It's 0.16, and it's in this particular direction. Now let's work on the red one, unless you have a question about the blue one. The thing I'm trying to emphasize is when we add and when we multiply, which you learn in school at elementary arithmetic in a different circumstance and have difficulties with, does the child, right? Now the child is also having some difficulties because it's a new world. But the general rule is that we multiply when the things can happen either successively or simultaneously, or independently like this. And we add when there are different possibilities for the same event that we can't distinguish by any experiment without changing the experiment. Here is the other alternative, the red ones. Okay, now I'm going to do the red ones. So this work here, this is rather a sloppy handling of the blackboard. I have to have curved pieces of blackboard. But the amplitude for the red one will now be calculated. To do that, I will have the amplitude that A goes into B. So I have a new arrow to work out, which I'll do in this, well, I don't know what color. It doesn't make any difference for the red amplitude. And I'll say that that is an arrow like this. And this arrow represents A to B. In a symmetrical position like that, if the distance between the detectors and the sources is very great, maybe you have some instinct about the relationship or the nature of this arrow compared to that. For example, how long is it? Nearly the same. Nearly the same. It's almost as easy if it's far away for the photon to come here as it is to come there. It's just about as likely. And the likelihood is the square of that if there was only one. So this length is very close to 0.4. It may be slightly less because it's off at an angle. Forget it. 0.39. Whatever's right, you put in right, but we're doing it sloppily. Now let's look, but what about the angle? Is it the same as this angle? You say, yeah, these distances are nearly the same. But remember, we're now talking, when we're talking angles, of millionths of inch. If these damn differences, these distances differ by a few millionths of an inch, it represents a couple of rotations. Not quite. It's 100 millionths of an inch, it's 2 rotations or something like that. So we have to be careful because even though these distances may be very large, so these are large, and these slopes, although they look almost the same on this drawing, we have to be accurate within a millionth, absolute millionth of an inch, and this is evidently longer. And therefore, although this was 1,600,000,000, I forgot the number that I told you. Can you remember? Have you taken notes? 0.18. 0.18 thing. This is 75,200,000,000. Anyway, you want to know, 0.72. And so I've drawn it at a different angle for that reason. And the purple one, I mean the other one, if the thing were perfectly symmetrical, will be likewise in the same direction. A rather simple case. You have to do the more complicated cases with different directions, but let's say it's that way. Now we have to get the total for this, the net result for the total amplitude for the red, which is obtained in what manner? By multiplying again. Same game. And in multiplying, we multiply 0.4 by 0.4, so we know that the length of it is 0.16, and there's where it is, and its length 0.16, right? You'll perhaps see that I probably written it in about the right place. If I consider my unit arrow, which ought to be in here in order to determine the angles, that wonderful unit arrow that helps you to decide what the angles were, and I really should be drawn from the same center. I tried to make this angle twice that angle, and I think it comes around to about there. And perhaps it would be better to draw it on the same piece of paper, on the same center, so that you can see that the angles are about double, okay? That is to say that this angle is this one, and again, same amount. So there's our answer for that. So we have the two pieces, the red one and the blue one. Since this is the red one, I better put it in red. Dumb, absolutely dumb. There it is, 0.16, and stick it out that way. Now, final, after all this work, what's the net result? Total. Total. Net result for the whole phenomenon, add these two arrows. Therefore, this total is equal to what you get by adding these two arrows. Right? And there they are. And we have to add, remember? Add. And you remember how to add. After all, this is 0.16. And this is 0.16. So the length, of course, is add, 32. No. And the angle is no. Forgot, you forgot. Add means you put the tail of one on the head of the other. The adding would be done and look like this. You'd put this here, and then you'd put that there, and you'd get the beautiful green sum. Notice I haven't made any green yet, so for excitement, I'll make something green if I had a green one. I haven't got a green one unless the black cap is on the green one. So I got two with black caps. That's what I'll make it yellow, so you can't see it. That's the total, and the square of that gives the probability, and that's it. What does that imply as a phenomenon? Oh, excuse me, I had a question? For the particular angles, actually.
Why there weren't two other alternatives
Yes.
for both photomultipliers going on
Yes.
one source?
Yes, I said at the very beginning, let us suppose that one comes from A and one comes from B. And I'll return to your question, which is not at all unimportant. Okay? Of what we do under those circumstances, whereas we can't make this rule. We don't have that condition, but I'll tell you later. Just let's stay where we are for a moment. Okay? Well, there's one thing left to say that's very interesting. Suppose we varied the separation of these. What would happen? We put these close together or we put them further apart? The angles are changing because the difference in distance between this one and this one, which is all that really counts, in millionths of an inch, is altering. And therefore the probabilities change. And so if you have two sources, and you can say that one comes from each one, and you measure the coincidence rate between two counters, the coincidence rate depends upon how far apart they are. It's very similar. Yes, very similar. It's confounded by the effect he's talking about. It's dirtied up by the case that they both came from A, which will turn out to be a uniform background. So it's bumps on that don't go all the way to zero. They go halfway down, up and down.
Do it very slowly,
Do what slow?
The source was very, very low intensity.
Yes, that's what I meant. It would still be, but you still can't determine that it's not two photons from one source unless you have apparatus up here to check that. Okay?
Another coincidence.
We'll come back to that question, right? So forget it. Suppose I knew I had some trick by which I was doing it so there was one photon from each source. Then I would get an intensity which varies. It turns out that if I don't have the trick, I also get an intensity which varies, but I haven't calculated it right. It varies, but it's not the same curve. It's a similar curve. It's a bumpy one that goes up and down between a maximum and minimum, but not maximum and zero.
It must be how an intensity interferometer works for doing it.
This is called the Hanbury
Brown twist.
twist effect because it was first realized that it would occur for radio receivers looking at radio waves from sources. And not only does it, you notice something else. If you move this and find these bumps, you can show that the distances and spacing for the various bumps also depends upon the spacing of the sources, as you can imagine. If these two sources are right on top of each other, moving that doesn't make any difference because the red and blue lines follow it. So It is therefore possible, by measuring these coincidences of photomultipliers, but in their case, it was a correlation of intensity measured by 2 radio receivers, but it's equivalent. The variation of this depends upon the spacing of the sources, and therefore is a technique for finding out whether something that you're looking at is one little dot or is more complicated, even when you don't have the magnifying power to be able to see it directly. You can see it by just moving radio receivers apart and together. It was a wonderful discovery. That can also be explained by a wave picture at that point, but the problem is, how do you understand it from quantum mechanics? This is the way we understand it. And it's been done with photons. It's even been done with photomultipliers with coincidences, so it's all known to be right. Okay?
Interesting thing about this is that form of interferometry requires two sources not to be coherent.
Yes, there's nothing special about these sources I didn't let one source interact with the other. I have 2 different photons. It must be distinguished. This is a kind of interference, you might say. That is, interference in the sense that in the end you're adding 2 amplitudes at different angles. That's called interference because you get funny bumps. You get funny bumps. Call it interference if you will. But you get funny bumps not through 2 different ways that one photon could go through a piece of equipment. That's called coherence or something. But 2 different photons that don't know what each other are doing, so to speak. Okay? And what I was trying to say about learning quantum mechanics is that in order to understand this process quantum mechanically the correct way, requires one additional feature that single waves don't. That there's a single arrow for 2 photons is an unexpected discovery for people who have been doing problems with 1 photon all the time because they thought that arrow somehow was attached to the photon, like the old idea that the photon was a wave and the wave was it. So that the new wave, the amplitudes for being found in different places, for a single photon is considered somehow attached to the photon. Only at the last minute you say, oh, well, it's a probability when you square it. But the fact is that these amplitudes work for very complicated processes, very many problems, many particles is 1 complex number, 1 amplitude, 1 arrow for the whole process, no matter how many parts there are in it. Okay, we've used up this time, and I can see, I'm just going to summarize what I'm going to try to do next time, because it's our last time, I believe, next time. So that there is a certain problem. You see, I can go on forever evolving and developing that thing. It would be nice to tell you something like what the rules look like for those special basic processes.
Don't we have 2 more times, tonight and tomorrow morning?
But tonight is one of those relatively easy times. I am at your service. We'll see how you feel tonight. But I also have to answer a question that somebody asked me. Can I design an experiment which will give those 3/4 and everything and those boxes and explain it to you through this mechanism which has exactly those numbers in it? I have to go home and design it. Reason is, the easy example is the polarization of light, which I didn't describe. And I don't want to go into describing that first and then explaining the case, but rather a more simple examples. More direct examples closer to the kind of thing we've been doing, and I have to design it a little bit. So it'll take me this afternoon to do that. So what I want to do is really 3 things. I want to do that example that we started with should be what we end with. It would be nice. Second, to tell you a little bit more precisely what the rules are for the fundamental processes, the 3 fundamental processes out of which everything is made. And finally, to say something important, and please somebody remind me that I want to talk about that, about what about the case that 2 photons come from the same source. It's an important thing to discuss, not an important for the calculation. It's an important point to be made, all right, on how to use amplitude. So I want to do those 3 things, and I hope you'll remind me to do them the next time we meet Friday. If tonight you're so anxious for more information that you won't be satisfied with talking about what makes trees grow or whatever we want to talk about, I'll do that. Okay. Okay. Everybody seems to vote for that. All right, I'll prepare another hard lecture for tonight. Okay?
We also want to do the class picture now.
The class picture,
Yeah,
yes.
class picture. And we also will be meeting here 2 to 4, and maybe dribbling over from 4 to
This often reminds me of a nursery school. One in the sense of having the drawing, everybody sitting in front of things drawing, you know.